Okay, by my watch, it's just about time to go, so let's get started. Talk today is going to be about Milkymist, the architecture for the open hardware world, and our guest today is Sébastien Bourdeauducq. Please give him an excellent, warm welcome.
Everybody, thank you for coming. So, as he said, what I'll be presenting today is a project on which I've been working for approximately 2 years and a half. I will give today a short introduction on how it all started, because it initially began as basically an embedded video jockey box, and it turned out to be a complete system-on-chip design. I mean, I really wanted to open everything. Then I will give a short introduction about what are the planned features of the initial design, what the VGA box was supposed to do. And then I will give a rough outline of the features of the system-on-chip that I have designed, or which I'm currently designing. Then I will move on to give some points, some very technical points about some aspects of the design that are quite challenging, because designing with video involves high-speed logic, computer architecture, many different domains. And I will just outline a few common problems that you can encounter if you want to build your own high-performance system-on-chip. And finally, I will give a short presentation of the software which you can run on it, for example, Linux or graphical user interface toolkit. And then I will finish with how you can develop yourself your own chip on an FPGA platform. So let's start with the introduction. So it started, as I said, as a device for video performance artists called VJs. It was inspired by the popular MilkDrop program for PCs. So MilkDrop is a plugin for Winamp, which displays in real time some visual effects coming from the music, which are rendered with graphics acceleration on your video card. And I wanted to integrate many interfaces because I began VJ like, I don't know, maybe 5 years ago or something. And I have built my own VJ software, which was never released because the code is awfully dirty. But it was based on MilkDrop, and I added many things. I wanted to make my performances interactive. So I did things like DMX control, MIDI control, or even control with the touch screen of a PDA. You could take your PDA and draw on the screen, and it was appearing in real time on the video's projection screen. This turned out to be quite popular in concerts. And I didn't want to carry around my tower computer with with big graphic cards, all the interfaces, USB switches. It turned out to be messy. And I thought it would be cool to have some very small embedded devices which would integrate all these things. And that's how I came up with the idea of building this embedded VG platform. So I wanted something at the frontier, somewhat between big computers with software to render visual effects, which I was using before, and a small handy microcontroller board, a bit like Arduino that most people know. So I will just give some examples of pictures you can get out from MilkDrop. This doesn't really do justice to MilkDrop because these are still pictures. If you see them moving in real time with music and some interactivity with MIDI, DMX, video, or anything, it gets much more impressive. So that's another type of visual effects you can get from MilkDrop. So, as I said, I wanted to make something which is really open hardware. I will take, for example, the Arduino, which is often touted as being open hardware. Well, basically, Arduino is just an IVR microchip, power supply, and connectors. And in this design, the IVR chip does all the magic. Everything that the Arduino does is basically done by the IVR. And the IVR is a black box. I mean, it's a chip in every sense. You have a plastic package, and you don't really know what's inside. So basically, Arduino isn't really open hardware, because on the other hand, you can describe all the logic which is inside the chip, and you can open source it. In this Atmel, they will never do that because the source code which is used at Atmel, in the Atmel company to build the IVR is trade secret, proprietary, whatever, or patented, even patented sometimes, and they will never open source it. But I wanted to make this VGA project a really open hardware thing, and that's why I went on to design my own chip. And this has also another technical advantage. This has also technical advantages. Because if I wanted to do it the traditional way, by using general purpose chips, I would need a very powerful and specific chip, for example, Texas Instruments OMAP, and this chip is well, it's proprietary, as I said, but it's even more proprietary than AVR because you have to sign sometimes NDA, you have binary only drivers sometimes, so it's really not a good solution for open hardware. And also, the advantage of making my own chip is that I can integrate all the interfaces. For example, I spoke of video inputs, I spoke of MIDI, of DMX. If I wanted to interface all this using a Texas Instruments OMAP chip, this would get awful because I would need many other chips on the PCB to take care of all these interfaces. So there are already some other projects which has went. Yeah, sorry, it doesn't work well. Yeah, thanks. Better. Okay. Yeah, so there are other open hardware projects which has went the same way. There is, for example, a grlib, which is developed by Auroflex Geissler. They are most well known for their Leon 3 processor, which is compatible with the Spark. It has been used by the European Space Station, for example. There is OpenSpark. Sun Microsystem is quite open source friendly, and they have released the source code for their Spark processor in Verilog. Unfortunately, it's very hard to use OpenSpark yourself because you need very big FPGAs. OpenSpark is a very complex design which has many optimizations, and sometimes when you are doing FPGA, it's better to have a more simpler processor which could run faster, because when you implement all the features which are in OpenSpark in an FPGA, you get very complex logic function with many levels, and the clock frequency goes very low, and it also eats up many FPGA resources. So OpenSpark is not very accessible to hobbyists. There is OpenGraphics. OpenGraphics is very ambitious. They want to build a graphics card for computers, which means it would compete with the high-end graphics card from NVIDIA and all the like. That's very difficult to do. And there is it's not really a fork, but it's close to Project VGA. It's also a graphics card, but it's a lot less ambitious than OpenGraphics because they don't want to make a complete graphics pipeline. So just basically want a frame buffer and VGA compatibility. Project VGA is really accessible. And there are other projects, for example, OpenRISC from OpenCores. So what I wanted to do is go the same way and build my own system-on-chip design for the Milkymist project. So I will just give now a short introduction of what the system-on-chip should do. So that's basically implementing MilkDrop, because my former VG program was also based on the MilkDrop system. So MilkDrop is working with an iterative rendering paradigm. So basically it takes the current image. You can start from black, for example, and you will distort it. So you have a set of equations that you can parameterize, and this will give a distortion to the image. You can zoom, you can rotate, you can scale, you can warp in any way you can. And once you have done it, you draw some waves, which are made from the music, and you draw some shapes as well, like polygons or anything, gradients. All this is parameterized by the music, or in my case, other interfaces such as DMX. For example, you could well imagine that the zoom is controlled by the lightning table with a slider on it. And once you have that, you display the result, and then you repeat the process over again. So the image gets distorted, and the wave gets drawn every time. And this gives the effect that I have shown before. Sometimes you can play with it to draw some fractal images, for example, or anything. Well, that's a bit simplified process, but the big picture is this, about the functioning of MilkDrop. So as I said, the distortion and the wave drawing are controlled by fully customizable equations, and this is called MilkDrop calls a preset. It's similar a bit to a patch in pure data. And by changing these equations, you have some parameters, for example, extracted from the sound, for example, the bass level, or the treble level, or the beat, or anything. You have these parameters in the equation, and you can combine them with a large panel of mathematical functions. So you write some equations, and you put them into MilkDrop, and it gets some nice visuals. And as I said, I want to add some DMX and MIDI interface, also OSC from Ethernet, and interaction with video. You could, for example, imagine a computer vision system reacting to video, or even some instead of taking a blank picture,